Good afternoon, everyone, and welcome. My name is Don Bailey. I'm chair of the Fellows Program here at RTI International, and it's my pleasure to welcome you to the inaugural lecture in our newly established RTI Distinguished Lectures series. This series is sponsored by the RTI Fellows Program, and the series is really designed to recognize truly outstanding individuals whose exemplary work is aligned with our mission. What is our mission? Improving the human condition. Excellent. And this talk is a great example of that. So it's only fitting that we kick off this series with a talk from one of our own, and I could see a lot of family reunion going on here in the pre-talk socialization. Blake Wilson. So Blake began his career at RTI in 1974. He started out as a research engineer, and for 33 years rapidly moved up through a variety of positions here at RTI as research engineer, as senior research engineer, head of the neurosciences program, director for the Center for Auditory Prosthesis Research, head of the neuroscience program, and director of the Center for Auditory and senior fellow. Many of his accomplishments during this time are described in a book that he and Michael Dorman published in 2012 entitled Better Hearing with Cochlear Implants, Studies at the Research Triangle Institute. So, you know what he's going to talk about. As surely you know from the title of his talk, Blake is the inventor of many of the speech processing strategies used with present-day cochlear implants. It's certainly one of the greatest, it's hard to overstate this, but it is one of the greatest achievements, I think, in modern medicine. Cochlear implants, you think about all our senses, vision, hearing, touch, smell, taste. Cochlear implants represent the first substantial restoration of human sense using a medical intervention. What a tremendous achievement, enabling high levels of speech recognition for the majority of users. Blake's widely published, and one of his papers published in Nature is by far the most highly cited publication in the field of cochlear implants. He served as the principal investigator for 26 projects, including 13 from NIH. I think we can all be envious of that. And he helped create the Duke Cochlear Implant Program in 1984 and the Duke Hearing Center in 2008. So I've read through his extensive CV. He and his collaborators have received numerous awards and honors, far too many to list here. But I'll mention two of them. Two recent awards, the 2015 Russ Prize for, quote, engineering cochlear implants that allow the deaf to hear, and the 2013 Lasker DeBakey Clinical Medical Research Award. I could spend the remainder of this hour detailing his many awards and accomplishments, but I know you'd rather hear from him in person as he presents his distinguished lecture toward better representation of sound from cochlear implants. Please join me in welcoming Professor Blake Wilson.
Well, thank you for your lovely introduction, and it's wonderful for me to be here among many of my former fellow fellows and many other friends in this audience, as Don mentioned. My talk today is about the development of the modern cochlear implant, and I'll mention that the success of the cochlear implant has been a surprise to almost every expert in ear surgery and auditory science. So many people made this advance possible, and I'll mention some of them. Today, cochlear implants allow high levels of speech recognition for the vast majority of their users. And here you see a wonderful, lively, fluid conversation between father and son that is enabled by the present-day cochlear implants. Bill Gates Sr. is having a lovely conversation with his son, made possible with the modern cochlear implant. So it's a major advance, and it's a surprising advance. So how did we get here? I think there were 4 large steps forward that enabled the development of the modern cochlear implant. And the 4 large steps are listed in this slide. The first step was to develop devices that could be safely used for a lifetime. These devices were primitive by today's standards, and they enabled an awareness of environmental sounds, but not many distinctions among those sounds, and were helpful as an adjunct to lip reading. So it turns out that the sounds that correspond to certain lip shapes can be very different. If I say red light, green light, the shapes on the lips are identical, but the sounds are very different. So even a crude representation of sound can be helpful in disambiguating the ambiguities of lip reading. And that's what these first devices did. The next large step forward was to provide multiple sites of stimulation within the inner ear. The inner ear is organized according to frequencies, where one end of the inner ear responds preferentially to high frequency sounds, and the other end responds preferentially to low frequency sounds, and places in between respond preferentially to intermediate frequencies. So to take advantage of this so-called tonotopic organization of the inner ear, and indeed the entire auditory system, one must stimulate different sites within the inner ear. So that was the next large step forward, is development of arrays of electrodes that could be safely inserted into the inner ear and stimulate these different sites along the length of the cochlea preferentially. But more needed to be done, and that was to utilize those different sites of stimulation in ways that were better than before. Initially, the multi-site implants didn't work very much better than the single-site implants, and new ways to utilize those multiple sites of stimulation had to be developed. And once they were developed, then the great majority of users could understand speech. A more recent step forward is to provide stimulation in addition to that presented by a cochlear implant on one side. And this can be done in one of two ways. One way is to provide electrical stimulation on both sides with two cochlear implants, bilateral cochlear implants. And the other way is to present acoustic stimuli for persons who have some residual hearing, usually at low frequencies. As it turns out, with the criteria for implant candidacy today, most patients who receive a cochlear implant have at least some residual hearing at low frequencies. So in retrospect, this turned out to be an important advance, because if you can utilize the natural hearing in addition to the prosthetic hearing, the benefits can be quite large, as I'll describe. So the pioneers made this possible in the face of vociferous criticism that I mentioned initially. And one of these pioneers was Dr. William House at the House Ear Institute in Los Angeles. He was the first to develop a cochlear implant that could be used outside the laboratory and for many years. He took by far most of the arrows of this criticism. And we as a field, and our patients, of course, have him and others like him to thank for providing the foundation for the subsequent development. So in the remainder of my talk, I'll describe the components of a cochlear prosthesis and also the function of a cochlear prosthesis. I'll say a little bit more about the history, especially those steps 2 through 4 that I just mentioned. I'll indicate the levels of performance today, and as I mentioned, the performance is surprising and excellent. I'll say a few words about the impact of the cochlear implant on society, the individuals that use cochlear implants, and their families. And then I'll offer a few concluding remarks at the end. In the right panel, you see a modern cochlear implant system that includes, well, this is not working for some reason. Can I have some help with this? Okay, I'll just describe it. You got it?
Got it.
I'm an electrical engineer and I can't make this thing work. I know the math. You know. So cochlear prosthesis system includes a microphone or some other means of input, such as a direct input from a MP3 player or a TV or anything that the person wishes to listen to. A computer within this behind-the-ear enclosure that analyzes the input sound and makes decisions about the patterns of electrical stimuli that should be delivered to the electrode array. Those decisions are transmitted across the skin radio frequency link, where this is the transmitting coil, and immediately beneath it and beneath the skin is an antenna that matches the outside antenna, and this implanted part is called the implanted receiver stimulator that takes the information from the radio frequency signal and decodes it and then generates the stimuli that are conveyed to an array of electrodes in the inner ear via a thin cable that passes through the bone. The electrode array is inserted into a chamber that goes along the length of the cochlea called the scala tympani. It happens to be highly surgically accessible. It's the largest of the three chambers that cover the length of the inner ear, and surgeons will tell you that this is a straightforward procedure. Of course, they say that about most procedures. So what is the function of a cochlear prosthesis? The left panel shows cartoons of a normally hearing ear and a deafened ear. And in the normally hearing ear, there is a structure that coils up through the helix of the inner ear called the basilar membrane. It's this light purple structure. And it's stiff and thin at the middle ear end and wide and flexible at the other end, the apex of the cochlea. And these different mechanical properties give rise to a filtering function such that the basilar membrane responds preferentially to high frequency sounds at this end and low frequency sounds at this end and intermediate frequencies in between. Right adjacent to this vibrating structure, the basilar membrane, are sensory hair cells whose cilia are sheared with displacements of the basilar membrane. Shearing of the cilia releases chemical transmitter substance into the synaptic cleft between the base of the sensory hair cells and the adjacent neurons of the auditory nerve. And if enough chemical transmitter substance is released, then those neurons are excited. So you can imagine that if a high frequency sound is present, then this part of the basilar membrane vibrates preferentially, shearing these cilia and stimulating these neurons whose neural impulses are conveyed and processed further in the brain. The principal cause of deafness is damage to or destruction of these sensory hair cells. They're fragile structures. They're subject to a wide range of genetic defects. They're subject to a wide range of what are called ototoxic drugs, that is, drugs that are poisonous to the inner ear. They attack the sensory hair cells preferentially, and sensory hair cells can be damaged by loud sounds, especially over a lifetime. And that's why many elderly persons have hearing problems. It's a condition called presbycusis, and it's the result principally of the accumulation of acoustic insults over a lifetime. So when the sensory hair cells are damaged or gone, there's a break in the chain that I just described, such that these neurons become silent because there's no excitation of the neurons from the vibrations of the basilar membrane. And the function of a cochlear implant is to bypass these damaged or missing hair cells and stimulate the neurons directly with electrical stimuli rather than chemical stimuli. And here, in the right panel, we see the business end of a cochlear implant. This is the array of electrodes that I described before. In this case, there are 12 of them along the length of the cochlea. You can count them, 1, 2, 3, 4, and so on. And the array of electrodes curls around the helical shape of the cochlea. Here we're looking at a top view of the cochlea, and here in these cartoons, a side view of the cochlea. Well, there are more than 3,500 of these hair cells distributed along the length of the basilar membrane in the normally hearing ear, but only 12 sites of stimulation with the cochlear implant, so you can appreciate immediately that there's a huge reduction in the fineness of the representation compared with what we have in normal hearing, 12 sites versus 3,500 sites. Also, the 12 sites don't compare favorably with the number of neurons that you have in the healthy auditory nerve, which exceeds 30,000. So 8 in the numerator and 30,000 in the denominator comes out to a pretty small number. And people at the beginning appreciated the smallness of this number and also appreciated the exquisite machinery of the inner ear that enables us to listen to the Ninth Symphony, to understand speech, to differentiate among all of those environmental sounds. And they basically said that reinstatement of useful hearing with crude and pervasive electrical stimuli was a fool's dream. Those stimuli and the patterns of neural responses that they elicit are vastly different than what we have in normal hearing. And this criticism persisted all the way up through step 3 that I mentioned before. And many of the statements were categorical. For example, the esteemed auditory physiologist Reinhard Klinke said in 1978 that from a physiological point of view, cochlear implants will not work. Well, I think that's a categorical statement. I got to know Reiner in later years, and I have the fondest memory of he, I, and Rainer Hartmann arranging a conference in Frankfurt to discuss further steps forward with the cochlear implant. So even Reinhard Klinke came around ultimately once it was clear that speech recognition could be restored. But at the beginning, tremendous resistance had to be overcome, and nearly every expert said, this thing can't possibly work. And despite the daunting magnitude of the task, multiple groups worldwide endeavored to develop a hearing prosthesis that would at least enable people to improve their lip reading ability and to recognize environmental sounds. And I mentioned Dr. House before. He was one of the from a news article about DeJourno and Ares in Paris, who had stimulated the exposed stump of the auditory nerve during an operative procedure electrically and elicited in this patient a range of auditory percepts. And a patient brought this news article to Dr. House in Los Angeles and said, hey, what do you think about this? Well, House had never heard of it. But he was so intrigued that he launched onto a lifelong quest to develop a prosthesis that could be used outside of the laboratory and for years. He knew that he had a range of auditory percepts to play with, and he developed the first useful device. The The persons who contributed to and teams who contributed to the different steps are indicated by the symbols, precursor to step 1 that I just mentioned, precursor to step 2, and step 1, house, and step 2, development of multi-site electrode arrays, indicated by the SS symbol. And you can see that there were multiple groups worldwide who worked to develop these multi-site implants. So they ignored the experts and pressed on. And the principal contributors to the development of multi-site implant systems are shown in this slide. On the left is Blair Simmons from Stanford University. In the middle is Ingeborg and Erwin Huckmeyer from the Medical University of Vienna and the Technical University of Vienna. And on the right is Graham Clark, who led a quite large effort in Melbourne, Australia. Blair Simmons in 1965 made a fundamental discovery, and that was that different pitches could be elicited with electrical stimuli applied at different sites in the auditory nerve with an array of electrodes implanted directly into the auditory nerve, but also different pitches could be elicited with different rates of stimulation at any one of those electrode positions, but only up to a certain point. So if a 200 pulses per second stimulus was delivered to one of the electrodes, the patient would almost always say, well, that's a low frequency sound, like a foghorn or something like that. And then if 250 hertz pulse train was presented to the same electrode, the patient would invariably say, that's higher in pitch. But if the rate was increased to 300, the patient would say, well, that's the same pitch that I just heard with 250. And for progressively higher rates of stimulation, the pitch remained constant. And this is what later became known as the pitch saturation limit for cochlear implants. There was a raging debate in auditory neuroscience at the time about which codes the brain uses to infer frequencies of stimulation. One camp had it that the different sites were responsible for the different frequency percepts or different pitch percepts. And the other camp said, well, the temporal variations are more important. Well, Simmons showed that they're both important, and they both operate, and he demonstrated the ranges over which they operate. Ingeborg and Erwin Huckmeyer developed the first microelectronic implant system that was used in conjunction with an array of electrodes held in a silicone carrier, and that device was implanted in December 1977. In retrospect, that device is the design prototype for the present-day cochlear implant systems. About a year later, Graham Clark and his team implanted a similar device at their hospital in Melbourne, Australia. Graham Clark also led a multidisciplinary team that investigated many of the aspects of electrically evoked hearing, safety of stimulation, more information about the place and rate codes, and how to develop electrode arrays that could be more focally stimulated. Ingeborg and Erwin Huckmeyer and Graham Clark were among the winners of the Lasker Award and the Russ Prize that Don mentioned earlier, and Blair Simmons is deceased. So where we were as of the late 1980s is well described by a principal conclusion from the first NIH Consensus Development Conference on cochlear implants. You may know that these consensus development conferences are conveyed on a wide range of topics such as cardiac disorders, cancer, and so forth, to advise physicians in the United States about the present state of care and to offer recommendations about which treatment should be applied and in which cases. So the consensus conference brings together experts in the respective field, and a consensus statement offers the recommendations that I just mentioned. One of the principal conclusions from the 1988 consensus statement on cochlear implants is presented on the left, and it says what I just said, that as of that time, there was some evidence that multi-site implants could be better than single-site implants, and that about 1 in 20 patients could carry out a conversation using the cochlear implant alone and without the assistance of lip reading. In the right panels are shown results from a study conducted by Rich Tyler and colleagues who traveled around the world testing the 10 best patients at each center that was responsible for developing different types of cochlear implant systems. And the type or site is indicated here. The Coromac device was developed by Professor Chouard and his team in Paris. The Symbiont device was developed by Professor Eddington and his colleagues at the University of Utah, and so on. You can see that the different devices perform at least somewhat differently. Again, these are the world's best patients at the time taking what are extremely easy tests by today's standards. And you can see that on average, the best of these provides about 35% correct sentence recognition, and the worst of them, no sentence recognition at all. It was a little dicey to conclude that multi-site implants were better than single-site implants because some of the single-site implants, the 3M Vienna device in particular, was just as good as several of the multi-site devices. Here, this nucleus device has 22 sites of stimulation within the inner ear, and this device has 1 site of stimulation within the inner ear, and you can see that the results are statistically identical. Also, this device had 12 sites of stimulation in the inner ear, but it was the worst and didn't compare favorably with the single-site system. So that conclusion was more of an expectation than a conclusion. It was obvious that these multiple sites had to be used in a better way to convey speech information. The circles show scores for the individual subjects. The red circles show chance performance, and the green circles show above chance performance. A few things to notice about these data are, first, that there's a wide range of outcomes with each of the devices, that only a few of the patients achieve speech recognition scores that are compatible with carrying out a conversation without lip reading. In these data, this one subject probably, and maybe these 2 subjects. Also, you can see a high preponderance of chance scores for identification of consonants for most of the devices as of the late 1980s. So my story and the story of our teams is presented in this article in Nature Medicine, which was included in the special issue of Nature Medicine celebrating the 2013 Lasker Awards. And on the left, you see our original RTI team. Charlie Finley is on your far left. I'm in the middle, and Dewey Lawson is on the right. Also, Bob Wolford was a member of our research team, and he's not shown here. You can see that the years have taken a little bit of a toll. I think that photo was taken in 1986 or thereabouts. We first conducted our patient studies in San Francisco. Our first NIH projects required a clinical collaborator, and at the time there were only 3 centers in the United States that were developing and applying cochlear implants, and they were all in California. One at the House Ear Institute that I mentioned, one at Stanford that I also mentioned, and the other at the University of California at San Francisco. So UCSF kindly agreed to work with us, and we built our equipment and developed our software here in North Carolina. Lugged that equipment on the plane. It was huge at the time. Took it out to San Francisco and conducted our patient studies there. Later, as I'll describe in a moment, we moved our studies to a small laboratory at Duke, and then ultimately to 2 laboratories here at the RTI. It was a wonderful journey, and one that I could not have anticipated, nor could I have ever guessed that cochlear implants work as well as they do today. Still, and this is not a scientific term, I think it's a miracle that cochlear implants work so well, because we know how sparse the representation is at the periphery compared to what we receive in normal hearing. And yet, somehow, the brain is able to take this sparse input and make sense of it, and make progressively better sense of it over time. So really, the present performance is a testament to the user's brains rather than any clever designs. But I also think we had to get above some threshold of quality and quantity of information to enable the brain to take over and do the rest. And that's the story of the development of the cochlear implant. So as I mentioned, we did our first work with patients at UCSF, and about a year into those studies, I received a call from Dr. Farmer at Duke. At the time, he was an otologic surgeon, and he later became the chief of otolaryngology, head and neck surgery at Duke. And we knew each other slightly. We had met a couple of times. I didn't know him well. And he called me up and he said, "Hey, Blake, I understand that you have this NIH project and you're conducting all of these studies with cochlear implant patients in San Francisco. How would you like to move those studies a little bit closer to home?" And of course, I was overjoyed with the idea. And he went on to say that if our RTI team would agree to do that, then Duke would initiate a clinical program to provide cochlear implants for deaf persons, and also hopefully a population of research subjects that we could work with. So that was the genesis of the laboratory at Duke. Dr. Sabiston, the chair of surgery at Duke, approved the laboratory, made space for us in the Baker House at Duke, if you're familiar with the topology of Duke. And he gave us a generous equipment grant to get started. So this was wonderful, and a big risk at the time, but visionary in retrospect. So Dr. Farmer is one of my all-time heroes. Unfortunately, he's also deceased, but I love him. And we got tremendous help from the RTI. 2 of the persons who helped us are shown here, but many others helped us too. The 2 persons shown are George Herbert on the left, who was president of RTI at the time, and Grace Boddy on the right, who was vice president and chief counsel at the time. One of the contributions they made was to help develop a policy to donate the results from our NIH-sponsored research on cochlear implants to the public domain. The idea being that any good idea or any large advance would be taken up by all of the companies that were then involved with the manufacture of cochlear implants, and thereby help the highest possible number of deaf and severely hearing impaired people. Well, at the time, there were only about 100 recipients of cochlear implants worldwide, and it didn't seem like that much of a risk. And it could give the field a little kickstart if we came up with a good idea. And all of those things came to pass. Today, there are more than 450,000 recipients of cochlear implants, compared with the around 100 when we started. But George and Grace crafted this policy and generously made the technology available for the benefit of deaf persons. It was a tremendous gift to humanity. And here is shown our small laboratory in the Baker House at Duke. On the left is Michael Piershala, who is a research subject who spent more than an integrated person year with us in helping us to develop new processing strategies for cochlear implants. And on the right is shown Dewey Lawson, who many of you know. And of course, he was a member of our core team. And here's one of our laboratories at the RTI. Those laboratories were set up in 1995 and remained in use through 2008. And shown on the left is Carol Tabor, another research subject who's taking a test of consonant identification. I don't think you may be able to see the different consonants on the screen from which she can choose when she hears a sound. And in the background is shown Bob Wolford, who I mentioned before. Here's a poster here for the 1995 consensus conference on cochlear implants held at the NIH, and I'll mention something about that a little bit later. The laboratories at RTI were wonderful. They were right adjacent to our offices and other facilities, and we had one laboratory for speech reception studies and the other laboratory for electrophysiological studies, where we would stimulate the auditory nerve in patients and measure the evoked neural response and learn about the conditions of their inner ears, and could use that information to customize processing strategies for those patients and learn more about how electrical stimuli can control the neural responses in the auditory nerve. So we had only one laboratory at Duke, but two laboratories at RTI, and the two laboratories were complementary. So we had developed a range of new processing strategies that were competitive with or a little bit better than the results that I showed you before. But in 1989, we developed a processing strategy that turned out to be a breakthrough in cochlear prosthesis development. And it's called the continuous interleave sampling strategy. This diagram is a diagram for engineers and looks a little bit daunting, but I'll walk you through it. The basic goal of the design is to present in the clearest possible way all of the information that can be perceived with electrical stimulation of the auditory nerve, and not make any decisions beforehand about what might be an important sound or what might not be an important sound, or to present less than the full amount of information. This goal trusted the brain to make the important decisions. Before, we had all sorts of engineering means to analyze speech and decide what was most important in the speech, and then just present that little bit of information. It turned out that our algorithms worked well in a completely quiet environment, but not so well in a typically noisy environment with high reverberation and in situations that we find ourselves in every day. So we knew that the brain had to be smarter than us, and so we put some trust in it. So this strategy includes multiple channels of sound processing, where this is one channel and this is the nth channel, and the only difference among the channels is in the frequency range that they analyze. So this is a bandpass filter that senses only low-frequency sounds, and this is a bandpass filter that senses only high-frequency sounds, and these intermediate bandpass filters sense intermediate ranges of frequencies. From each bandpass filter output, we sense the energy over time, and this is called the band envelope, which in this case is done with a rectifier followed by a low-pass filter. That's to engineering components that just indicate one way to sense the energy variations in a band of frequencies. Much more complicated ways can be presented. This is the simplest, and it works well, which is followed by a nonlinear mapping function. So the dynamic range we have in normal hearing is many million-fold from just hearing a sound to standing next to a jet engine. In contrast, with electrically evoked hearing, it's only 2 or 3-fold from just hearing a sound to a sound that's intolerably loud. So you must somehow compress this wide range of sounds that you have in the environment into the very narrow dynamic range of electrically evoked hearing, and that's the function of this nonlinear mapping function. So these energy variations are sensed only up to about 400 hertz, that pitch saturation limit I mentioned before. That's the most temporal information that you can present at a single site of stimulation. So in this envelope detector, this low-pass frequency, low-pass filter frequency is set at 400 hertz, such that the low-pass filter passes all signals below 400 hertz and rejects all signals above 400 hertz, limiting the amount of temporal variations to below 400 hertz and below the pitch saturation limit for each of the channels. The outputs of each of the channels are directed to different electrodes in the implant corresponding to their bandpass analysis range. So for these low-frequency sounds that are sensed in the environment, the output of all of this processing is directed to the apical-most electrode in the implanted array of electrodes. And in contrast, the channel that senses high-frequency sounds sends its output to the basal-most of the electrodes, respecting this tonotopic organization of the auditory system that I mentioned before. So both place of stimulation and frequency of stimulation are represented fully with this strategy. A signal processing trick that is used is to interlace the stimuli across time such that no one stimulus is accompanied by another. You see a small offset in the timing of these stimuli. And this is important because if you present the stimuli simultaneously, the electric fields add across the electrodes and produce tremendous interference or crosstalk among the electrodes and degrade the representation of this place cue that I mentioned. The cochlea is about the size of a pea, and it's filled with highly conductive fluid. So stimulating different sites selectively is a huge engineering challenge. That's the worst possible situation. So this interlacing of stimuli was important to diminish the effect of the small size and the immersion in highly conductive fluids. This slide shows the first results comparing this new sound processing strategy with the best of what was available before. You might remember that bar graph, and on the far right of the bar graph was the highest bar. Well, we selected the 7 patients in the world who had the best performance with that particular device and compared it with the new sound processing system. So they were using their clinical compressed analog processors that did present stimuli simultaneously, and they were immediately tested with the new sound processing strategy, continuous interleave sampling. Each patient had more than a year of daily experience with their compressed analog system at the time of the test, and less than an hour of informal conversation with the new processing strategy. So these 7 subjects that were selected for their high levels of performance are shown with the green lines, and subjects with more typical levels of performance were tested later, and their results are shown with the blue lines. In both cases, you can see for all tests, recognition of 2-syllable words, recognition of relatively simple high context sentences, recognition of more difficult sentences, and recognition of monosyllabic words, that each and every subject showed an immediate and huge improvement in speech reception with application of the new sound processing strategy. So when we played this, people would say things, "Oh, now you've got it," or "Hot damn, I want to take this one home with me." Then we knew we had something. So this was a huge jump forward in utilizing those different sites of stimulation better than before. This strategy is still in widespread use today and is the model for subsequently developed strategies. So with the WISE policy that Mr. Herbert and Mrs. Boddy developed, this new advance was almost immediately taken up by the manufacturers, and each of the major manufacturers implemented the new strategy in their cochlear implant systems. This slide shows results from one of the first clinical trials with a device developed by the Med-El company in Innsbruck, Austria, that included 55 adults who lost their hearing after acquiring language, that is postlingually deaf, whose scores are shown by the circles for different times after the initial fitting of the cochlear implant system following the surgery. So this is 1 month after the initial fitting in the left column, 3 months out to 2 years for recognition of sentences and recognition of monosyllabic single-syllable words. Recognition of sentences is easier because it has contextual cues, and recognition of monosyllabic words is the most difficult test given in standard audiologic practice. You can see in both sets of data that there seems to be an improvement in scores over time, out to at least 1 year. Also here, you can see that the great majority of patients are scoring at 80% correct or higher in the recognition of everyday sentences. This is completely compatible with conversations on your cell or landline phone, a lawyer able to practice in the courtroom, persons able to do different jobs that require hearing, and much higher interaction among family members. So with these scores, useful communication is restored. The scores for monosyllabic words are lower because the test is more difficult, but the test is also less relevant to everyday communications. You can see the improvement over time a little bit better in the right column, which shows the means and standard errors of the means for the sentence test with the open circles and the monosyllabic word test with the closed symbols. Both sets of data show improvements in scores out to about 1 year post-fitting, which implicates the brain as playing a major role in producing these wonderful results that we have with cochlear implants. That is, the brain is able to take a decidedly sparse input at the beginning and make sense of it, and to improve and to make progressively better sense of it over time. This is an effect that the neuroscientists call brain plasticity. It's a reknitting of brain function to utilize a novel input or a sparse input. And again, the performance is as much a testament to the brain as anything else. And I mentioned too that the more recent step forward is to provide stimuli in addition to the electrical stimuli that are presented by a cochlear implant on one side. And this can be done in the two ways that I mentioned. The first way is to present electrical stimuli to both sides. And here we see the first child recipient of bilateral cochlear implants, or to present acoustic stimuli in combination with electric stimuli, where you can see the hearing aid acoustic driver here and the other parts of the cochlear implant system that I described before here and here. And it turns out that the acoustic stimulus can be delivered to either side, the side with the cochlear implant or the other side or to both ears, and produce the same sorts of beneficial effects if the residual hearing on the two sides is comparable. And this slide shows or indicates the benefit of this type of adjunctive stimulation, in this case for combined electric and acoustic stimulation of the auditory system. Here, 15 patients were studied with full insertions of an electrode array on one side and residual hearing at low frequencies on the opposite side. And also shown here for reference are results from the study that I showed you before for recognition of monosyllabic words with electrical stimulation only, whose results were reported in 1997. This study was conducted in 2008. And you can see that with electrical stimulation alone, there's not much movement, even though here new types of processing strategies are used. The criteria for implant candidacy have been relaxed, and more channels and sites of stimulation have been included in these cochlear implant systems, but no change. In contrast, when you add the acoustic stimulus, you see a substantial improvement in scores, highly statistically significant improvement in scores, and the major effect is to bring the bottom of this range upward. So this is a wonderful advance that actually helps a majority of cochlear implant patients today. Similar benefits are obtained with electrical stimulation on both sides, and electrical stimulation on both sides also provides an added benefit of sound localization abilities. So in normal hearing, the way we lateralize sounds in the environment are by the tiny differences in amplitude and arrival of sounds at the two ears depending on location. So if I have a sound source off to my right, this ear receives the signal first, and it receives a somewhat louder signal compared with the ear on the other side. And the brain can use that information to decide that, yes, in fact, this sound came from off to the right side. You have to have balanced stimulation on both sides to represent those cues, and that's something that bilateral cochlear implants can do. So I mentioned before that this thing has taken off in a really surprising way. Initially, there were many doubters, and the number of persons receiving a cochlear implant was quite small, all the way up to the late 1980s. And here I've also shown the 4 large steps forward: the development of devices that could be applied over a patient's lifetime, the development of devices that could provide multiple sites of stimulation in the inner ear, the development of new processing strategies that use those multiple sites better than before, and the advent of adjunctive stimulation. Each of these dots shows a published datum for the indicated time for the number of persons receiving a cochlear implant in thousands. So this is 350,000. For some reason, this slide is cut off, so you can't see the label here, but this is 350,000, and of course, this is zip. If you fit an exponential curve to these data points, the correlation coefficient is higher than 0.99. So the growth is perfectly exponential. And if that growth continues, more than 1 million people will have received a cochlear implant by early 2020. And as Don so kindly mentioned before, these studies that I've just described in our laboratories are presented in much greater detail in this book that was published in 2012. And for the technically minded among you, you might like to see this book. Play the video, please. Now I would like to show a short video of Dr. Tusi at Duke and one of her implant patients.
When I first started in practice in the mid-'80s, all right, let me take a peek in here. We didn't have anything to offer children who were born deaf.
When Walter was born, he was born deaf in his left ear. About the age of 2, he started losing the hearing in his right ear, and he lost it rather quickly.
I'm doing good.
I'm so glad you came here. It's so good to see you.
For children born with profound deafness, receiving bilateral implants during their first years
It's been good.
You gonna sit next to me?
Yeah?
Yeah?
provide a life of hearing never dreamed possible.
Trains. Do you have toy trains like Thomas?
I like playing with toy trains.
It's made a big difference in his life. He's able to go to mainstream school. He's in a regular classroom. What would you like to say?
I like to say, I love you.
Why do you love Dr. TC?
I love her because she fixed my ears.
It's a privilege. It's a joy. You know, it's the biggest joy of my professional career to be able to do a cochlear implant in a child who can't hear and know that he or she will grow up to have normal hearing. It's a profound joy. This is really a miracle.
The many people and organizations It's off. It's off. It's off. It's off. School at Duke, and I had spectacular teachers there who took me under their broad wings. One of whom is Bill Joines, who is shown with me in the left photo. And of course, all of my coworkers in the teams over the years made the work possible. We had continuous support from the National Institutes of Health for more than 2 decades. Spectacular support from RTI, Duke, and UCSF. We continued our partnership with UCSF after we moved the laboratory to Duke. We had support from all of the major companies that manufacture cochlear prostheses, and multiple of our inventions are used in each of the prostheses available today. Thanks again to the policy that George and Grace developed. We've enjoyed wonderful partnerships with groups worldwide, including 27 universities worldwide, but also with 5 or 6 other research organizations. And last but not least is the support from my wonderful family. Many of you will recognize Dr. Doris Rouse in the upper right photo, and she and my daughters have helped me every step of the way. I'm such a lucky guy. Thank you.
I think they can hear.
You can hear, yeah. Well, you got
So, you put a chart with the one.
Yes.
Is it possible that those data are from random? Possible to feed program signal to make the
Such a wonderful question, and something that we're thinking about now for smart training procedures, as you alluded to, could greatly accelerate that growth. Also, it's been recently discovered that some adjunctive drug treatments that are used in conjunction with smart training procedures can accelerate the learning even faster. So there's some drugs that can make the brain more adaptable for a short period of time, and safely so. And if those drugs are administered at the time of the testing, then the rate of growth can be doubled, we've learned. So great question and a current topic of research.
Blake, I'm sure you are familiar with your thing, the use of deep brain stimulation for Parkinson's and major depression, and possibly even applying to drug abuse. With the increase in technology with electronics, is it going to be able, in the future, you think, to be able to do that without having the brain penetration?
I think you have to get the electrical stimulus to the site somehow.
So you're not going to be able to get it without getting there.
Right.
Okay.
But there are advances in electrode design that make the insertion less traumatic. And so the procedure is even safer, and the results from those treatments have been absolutely remarkable. And in fact, deep brain stimulation was honored by the Lasker Award that followed ours.
I know that newborn screening programs throughout the United States now include hearing screening in them, and so many infants are identified at birth or shortly thereafter with hearing problems. And so a couple of questions related to that. Do you know what percent of, about what's the average age of a cochlear implant for a baby? Do they have to have repeated implants over time to as they grow? How long do these things last, et cetera?
Ideally, and oftentimes they can last for decades. And a fortunate circumstance is that the size of the inner ear is adult size at birth. So you can safely implant a cochlear implant system for a child who's less than 1 year old and have the full expectation that that child will be using the same implant device 20, 30 years later. There's also a moral imperative now to implant children as soon as possible and as soon after they've been diagnosed as being deaf as possible, because we now know the great importance of brain plasticity and also reorganization of the brain that occurs later in life with the absence of a sensory input. This is an effect called cross-modal plasticity. It turns out that children who are implanted about before the age 3, or 2 perform very, very much better than children who are implanted after about age 5. And that's all due to these changes in brain function that occur early in life. So we didn't know that before, and there was always great caution in implanting infants, right? But now we know that that's absolutely the smartest thing to do. You know, a remarkable thing about these children who receive cochlear implants is that they can enter into mainstream education without any special assistance. They can function with their families like a normally hearing child. It's just incredible to see it. Right, so electrically evoked potentials, brain waves, have been measured, but not brain imaging. And the reason is that there's a magnet in the implanted receiver stimulator that holds the transmitting coil in place over the implanted receiving stimulator. And so that magnet could be pulled out of the head with an MRI machine, or produce, at lower levels, produce huge image artifacts in the picture.
Like a chemical question, in one of your introductory slides, you indicated neurotransmitters going down those fibers. What are the neurotransmitters? Which ones?
Yeah, glutamate is one.
Any dopamine?
I don't think so, Ivy, but I'm not sure. I'm an electrical engineer, right? Didn't you hear that?
Along those lines, how selective this simulation to this hearing receptors versus other receptors?
Say that again, please.
How selective this simulation, electric simulation, to this hearing actually receptors versus others? Are we seeing any off-target, like touching other receptors in the brain, or just specific to this hearing receptors? And then my second question, if you don't mind, is there any side effect seen after using, like a headache or something related like that?
Right. So in the early days, when electrode designs were not as advanced as today, there could be, in scattered cases, stimulation outside of the auditory system. So one stimulation is a stimulation of the chordotympany nerve that runs right outside the cochlea that affects taste. So some patients had a metallic taste with that. There also have been some balance disturbances, especially in the early days, stimulating the nearby vestibular system. And in some cases, there can be a small facial twitch because the facial nerve runs right through that region. Now, electrodes are placed a little bit closer to the target auditory neurons, and we have better control over the patterns of stimulation. So extra auditory stimulation nowadays is quite rare.
For your talk. Could you talk a little bit about the role of the deaf community and your experience with their advocacy either for or against cochlear implantation?
Yeah, happily. The attitude has changed over the years. Initially, when cochlear implants didn't work too well, persons in the deaf community were asking, why should this treatment be applied, especially for children, to take my child out of a wonderfully supportive and warm environment of the deaf community. And they were quite, some members of the deaf community were quite adamant about this. And protested in various ways. I can remember I was at a conference in Paris in 1995, and members of the deaf community came into the conference. This was a conference on cochlear implants. They came into the conference blowing police whistles to completely disrupt the proceedings. I can't imagine that happening today because the performance has improved so much that nearly every parent of a deaf child wants the deaf child to have access to hearing, especially hearing parents of deaf children. Deaf parents of deaf children may wish to retain the warmth and the richness of the deaf culture. Today, I'm not aware of any protests, and even at places like Gallaudet, which is the university in the United States for deaf and severely hearing impaired persons, around half the students now have cochlear implants. So the attitude has changed over the years.
Very nice talk. Quite amazed with the fact that you mentioned about how the brain processes signals. I'm wondering how this performs as people age and when there's long-term memory loss. And the other question is, how does this work with maybe mentally challenged children if brain is kind of if we are relying on the brain to process those signals?
Well, those are such great questions. One of the happy findings is that elderly persons, and by elderly I mean in the 80s, who receive cochlear implants perform just as well as younger persons receiving a cochlear implant. So that's a real happy outcome. Many multiply handicapped children have received cochlear implants, and the results have generally been favorable, but not always favorable. And a possible reason is that there are differences in brain function among those recipients. You can turn the question upside down and ask about hearing loss and dementia. Recently, it's been demonstrated that there's a highly significant association between hearing loss and dementia in elderly persons. And even more recently, it's been shown that application of a cochlear implant can improve cognitive function for a severely hearing impaired person who's aged, say, 70 or older. So this is another moral imperative, and that is to provide better treatments for hearing loss among our aging population to forestall, insofar as possible, the onset and continuation of dementia.
Does insurance cover?
Yeah, it's so paradoxical. Insurance covers cochlear implants, which is an expensive surgical procedure and an expensive device, but does not cover hearing aids. And so well over 20 million people in the United States can benefit from a hearing aid, and several 100,000 from a cochlear implant, but cochlear implants are covered.
Thank you again for being our inaugural lecturer. We really appreciate it. It was a great talk, and I was really impressed with your ability to convey complex information to even I could understand it. So I appreciate that. We admire your accomplishments. We're proud to call you one of our own.
I'm proud to be one of your own.
And appreciate everything that you've done to improve the human condition. Clearly, you've lived that motto. We have a little gift for you to remember us by, and also there's a very nice check in here, so don't lose this bag. In fact, we'll hold on to it for you in just a minute if you'd like. So I do need to thank several people before we stop. So first of all, is Monica still in the room? Monica Hall is out and she's out, of course, working, getting things ready for the reception. Monica is my administrative assistant, and She's the person who works behind the scenes to keep everything working well and supporting the Fellows Program. So please say hi to Monica when you go out and thank her. I'd like to thank the AV people who've been very helpful in making things work today. Within the Fellows Program, we have a committee chaired by Robert Beach and Tony Hickey that helps to plan and lead the seminar series and distinguished lecture series. So this will be the first in a number of these. We'll probably be having 2 of these a year. So we'll look forward to future announcements about upcoming events. I want to thank the RTP Foundation for this great facility and for RTI for supporting the work that goes on there and for supporting this event. So please join me again in thanking Blake for a great talk. And Blake will be here to visit, so please go out into the foyer and help yourself to some snacks and chat.
Yes, and let me thank you for being such a great audience.
Would you like me to hold on to this so you can chat and visit?
Thanks.
And if I'm not here, Monica will have it.
Okay.
So that was super. That was fantastic. Very inspirational.
Oh, well, thank you.